Hello and welcome to Engineering Safari. Today we'll be covering the topic combinational logic circuits. So this is the third module of digital system design. So I'm assuming that everyone watching this is familiar with the basic topics of digital logic like binary addition, binary subtraction, the representation of each logic gate, how KMAPS are made, and how truth tables are written. So if anyone is not familiar, they can just watch the short videos that we've made on YouTube and come to this video after that. So the topics that we'll be covering in this module are all related to various combinational logic circuits, and we'll also be seeing topics about how we can make our own logic circuits for any given expression or any given encoder. So the first topics that we'll be talking about are half adder and full adder. Then we'll move to half and full subtractor. Then we'll talk about multiplexer, demultiplexer, and how they're used to simplify Boolean expressions. Then we'll talk about encoder and decoder, and similar to mux, how they are also applied in day-to-day circuits. And the last topic is parity generator and parity checker. We'll talk about both even and odd parity. So for each of these combination circuits, we'll talk about the truth table, how we represent each of them using logic gates, and how they are actually useful to us and how they help us in making simpler circuits. So with that said, the first topic that we're talking about is half and full adder. So in half adder, we just add two numbers. So let's say we have A and B. And for every addition, every binary addition, we get a sum and a carry, right? So zero, if both the inputs are zero, so upon adding these two, we get zero in the sum and zero in carry as well. And then let's take one of the inputs as 0 and 1. The addition of 0 and 1 gives us 1 with no carry. So we have 0 in the carry. Similarly, 1 and 0 is also going to be the same addition, which gives us 1 as the sum with no carry. Adding 1 and 1, however, gives us a carry of 1 along with 1 in the sum. So now that we've written the sum and it gives us 0 in the sum along with 1 in the carry. So now what we need to do is we need to represent the sum and the carry in terms of the input. So like you can see 0, 1, 1 and 0. This is how the truth table for an XOR gate looks like. So we can say that sum is A XOR B, and for carry, like you can see, 0, 0, 0 and 1 is the truth table for an AND gate where the output comes out to be 1 only if both the inputs are 1. So carry is given by A plus B. So the logic gate representation for this would be A, A and B passed through an XOR gate gives us sum, while A and B passed through an AND gate gives us the carry. So this was addition. This was about the addition of two inputs. So for three inputs, we use a little more complicated version of an adder called the full adder. So here we are given three inputs, and similar to what we did for an adder, we take the sum and carry for each of for each possible input, and then we represent the sum and carry using logic gates. So again, if we have all three inputs as 0, the sum of all of them gives us 0 in the sum and 0 in the carry. Now if one of them becomes 1, we have 1 in the sum with no carry. And then if we have 0, 1 and 0, This again gives us 1 in the sum with no carry. Next, we have 0, 1, 1, which 1 plus 1, like we saw, gives us 0 in the sum and 1 as carry. Then we have 1, 0, 0. So the sum of this gives us sum 1 with no carry. Then we have 1, 0, 1, which gives us, which is again 1 plus 0 gives us 1, and 1 plus 1 gives us 0 with a carry. Then we have 1, 1, 0. So 1 plus 1 gives us 0 as sum, and 0 plus 0 gives us 0. And the carry that we got from the sum of these two ones will be will be written under carry. So there isn't space for the last one. So the last possible input that we can take is 1, 1, 1, where all the three inputs are 1. So this gives us 1 plus 1 basically gives us 0, and 0 plus 1 gives us 1. So we have 1 in the sum, and the carry from the addition of the first two ones will be written under the carry. Right. So this is the final expression that we have. So we have 0, 1, 1, 0, 1, 0, 0, 1 under sum, and under carry we have 0, 0, 0, 1, 0, 1, 1, and 1. So unlike the previous one, we can't just look at the truth table and come out with a definitive logic gate circuit. So for this, we'll draw the KMAP separately. And using the KMAP, once we simplify the possible Boolean expression, we can make the circuit. So let's say we have A and BC input here. So this will be B complement, C complement, B complement C, BC, and BC complement. This is A complement and A. Right. So for 0, 0, 0, we are only making this for sum. So for 0, 0, 0, we have 0. For 0, 0, 1, which is A complement, B complement, C, we have 1. For 0, 1, 0, which is A complement, B, C complement, we again have 1. Then the next one is for A, B complement, C complement. So A, B complement, C complement is again 1. And then the next one is for A, B, C, which is here. And the others are 0. So this configuration is called the chessboard configuration, where you have alternate zeros and ones. So whenever you have the chessboard configuration, it means that it's the KMAP for a XOR gate. So this can be simplified and written as A XOR B XOR C. So this is what gives us the sum of a full adder. So for carry, which is C out, let's see the, let's make a new KMAP. This is A complement and this is A. This is B complement, C complement, B complement, C, BC and BC complement. Okay, so here we have a 1 for A complement, BC. A complement and BC is 1. And of course, A, B, C is 1, 2. And then we have a 1 for A, B, A, B complement C and A, B, C complement. So for A, B complement C, we have a 1, and for A, B, C complement, we have another 1. So now what we do is let's take these three groupings of ones to simplify our KMAP. And upon grouping this, the first grouping gives us DC. This particular grouping gives us AC, and this grouping gives us AB. So uh, this gives us BC plus AC plus AB. However, like you can see, this type of grouping does not give us a definitive result. So what we do is, uh, since the conventional grouping for KMAP doesn't work here, we just group the central ones. And no, sorry, we just group the one which gives us AB and leave the other two expressions, this one and this one, as it is. We just take the AB grouping and discard these two groupings, and that helps us write this in the form of a logical circuit mode. So you have AB plus, this is A complement BC, and this one is A B complement C. So now we have AB plus C. We take C common, we get A complement B plus AB complement. Right. So this gives us AB plus C, and A complement B plus AB complement gives us A XOR B. So this type of grouping is not something which is logical or which is applied anywhere else. We just take this grouping in this particular case because it helps us arrive at this logical arrive at this type of an expression that can easily be expressed using gates. So this is the expression for carry out. So now if you have to express it using gates, we know that sum is A XOR B XOR C. So we take all three of them, and A and B are first taken through an XOR, and their output is taken in XOR with C. And this gives us the sum of a full adder. And for carry out, we know that we take A and B in an AND gate, then we take A XOR B and then take it in an AND gate with C, and then the final product is taken in an OR gate. So let's do that. So A and B are both taken in an AND gate. Then we have A XOR B that is taken in an AND gate with C input. And the outputs that are a result of these AND gates are taken through an OR gate, and that gives us the carry out of a full adder. So I hope that's fine. So the next type of combinational circuit that we'll talk about is a half subtractor. So the same way we performed addition using a half adder and a full adder, the same thing will be done, but what we'll be performing is subtraction of the given binary numbers. So half subtractor. So in half subtractor, we'll be performing the subtraction of two inputs, and the full subtractor will be for performing subtraction of three inputs. So we take A and B, and then the difference and borrow. So for 0 and 0, 0 minus 0 gives us 0 in the difference with no borrow. Then we have 0 and 1. So 0 minus 1 gives us 1 along with a borrow of 1. So that is 0 minus 1. And 1 minus 0 is just 1 in the difference with no borrow. 1 minus 1 is again going to give us 0 in the difference as well as borrow. So like you can see this is the expression for the difference expression like I mentioned in adder is the truth table for an XOR gate. So D is equal to A XOR B. And for borrow, you can see that it's just A into B complement. So borrow is given by AB complement. Sorry, it's A complement B. Like you can see for the only time you are actually getting an output is when A is 0 and B is 1. So the final result in terms of expression in terms of an expression is A complement B. So if we have to draw the truth table for this, I mean the logic gate expression for this, we take A and B through an XOR gate, and that is the difference, and A and B, A complement into B gives us the borrow. Okay, I hope that was clear. So now that we found the subtraction for two inputs, let's see how we can find the subtraction for three given inputs using a full subtractor. So here we have A, B, and C, and again we have a difference and a borrow. So the first possible inputs that we can take are 0, 0, and 0. So 0 minus 0 gives us 0 in the difference along with no borrow. Then we have 0, 0, 1. So 0 minus 0 gives us 0, and 0 minus 1 gives us 1 along with a borrow which is taken. Then we have 0, 1, and 0. So 0 minus 1 again gives the difference of 1 along with a borrow, and 1 which was the difference here. 1 minus 0 gives us 1 itself. So again we have 1 in the difference and 1 in borrow. Then we have 0, 1, and 1. So here 0 minus 1 gives us 1 as the difference and 1 in borrow. So we write the borrow here. However, 1 minus 1 gives us 0. So the entire difference comes out to be 0 here. So next we have 1, 0, 0. So 1 minus 0 is 1, and again 1 minus 0 is 1 itself. So we have 1 in the difference with no borrow. Then we have 1, 0, 1. So 1 minus 0 is 1, and again 1 minus the result from the first two subtractions, which is 1. 1 minus 1 gives us 0 in difference and 0 in the borrow. Then we have 1, 1, 0. So 1 minus 1 is 0, and 0 minus 0 again gives us 0 in the difference and 0 in the borrow. Then we have 1, 1, and 1. So 1 minus 1 gives us 0, and then 0 minus 1 gives us difference of 1 along with a borrow. So this is the truth table for a full subtractor. So now let's again use a KMAP to try and find the simplified expression and then implement it using logic gates. So we again have A complement A, B complement C complement, B complement C, B C, and B C complement. So this is the one for only for difference. So for difference we have 1 for A complement B complement C and A complement B C complement. So we have ones in A complement B complement C and A complement B C complement. Then we have another one for A B complement C complement and for ABC. So A B complement C complement and ABC. So like I mentioned for full adder, This configuration with alternating zeros and ones is called the chessboard configuration, and that is the K-map only for an XOR gate. So this is given by A XOR B XOR C, right? Okay. And for borrow, now let's find the K-map for borrow as well. This is A complement A, B complement C complement, complement C, BC, and BC complement. Okay, so here we have one for A complement, B complement C, A complement B, C complement, and A complement B, C. So one along with a one for ABC. So these are the three ones that we have. Okay, so again, like I mentioned for half adder, for full adder, the normal way of grouping K-maps is not going to help us get an actual simple logic gate diagram. So what we do is we group these two ones alone, and these two ones are taken as it is. So we have A complement B plus A complement B complement C, which is this one, and then ABC. So now we have A complement B plus we take C common here, and we have AB plus A complement B complement. So this is A complement B plus C A XNOR of B. Okay, so this is the borrow out for a for a full subtractor. So now let's represent them using logic diagrams. So for difference, you have A and B that pass through an XOR gate, and the output from this XOR gate is taken along with C into the second XOR gate. That gives us the difference. Then for borrow out, we have A complement, so a NOT gate along with B, these two to an AND gate, and then we have let's take this XOR A XOR B through a NOT gate gives us A XNOR. We multiply that with C, and these two AND gates, the output from these two AND gates is then taken through an OR gate. So the output of all of this is the borrow out. So that's all about full subtractor. So far we have seen how we can add two binary inputs, add three binary inputs, subtract two binary inputs, and then subtract three binary inputs. So now we'll have a look at multiplexer and demultiplexer. So multiplexer in short is written as MUX. So what a multiplexer does is it serves as a data selector for us. So there are multiple data inputs which are passed through a MUX, and with the help of select lines, based on the based on what is actually fed to these select lines, a particular one of these inputs is selected as the output. So in a MUX, you always have n inputs and you have m select lines. So the number of inputs is always equal to 2 to the power m select line, 2 to the power m, where m is the number of select lines and n is the number of input lines. And you always have just one output. So if we have two select lines, that means we have 2 to the power 2 inputs, which is 4 inputs. So this is called a 4 is to 1 mux because you have 4 inputs and just one output. So here you have S1 and S0, which are the select lines. These are I0, I1, I2, I3. So depending on what is actually fed into these select lines, one input gets chosen and that comes out as the output. So let's say we have 0 if the value of S1 is 0 and the value of S2 is 0 as well. What that means is whatever is the value of input I0, that's what comes out as the output. So the output will be I0 in this case. So if you have 0 and 1, then the second input line, that is I1, that will directly be fed into the output and that comes out as the output. So 1 0 means the third input line gets selected as the output, and 1 1 means the last output line gets selected as the output. So that is the function of these select lines. So if we look at a simpler version of this, that is the 2 cross 1 mux, you have just one select line, I0 and I1. So if S0 is 0, then the output will be I0, and if S0 is 1, then the output will be I1. So basically, whatever is the binary value of these select lines, that's what enables us to choose one particular input line as the output. So uh, the first thing, the first application of mux, not exactly an application, the first uh, problem that we learn about mux is how we can implement a higher order mux using lower order mux. So let us have a look at 8 cross 1 mux using 4 cross 1 mux. No, let's take 8 cross 1 using 2 cross 1 mux. Or to just begin with a simpler one, let's implement the 4 cross 1 mux first and then the 2 cross 1 mux. So the first thing that we have to do is we have to see how many 2 cross 1 muxes are actually necessary to make a 4 cross 1 mux. So what we do is we take the value of n here and go on dividing it by the value of n here. So 4 by 2 gives us 2, and then again dividing 2 by 2 gives us 1. So basically first we need two multiplexers, and then the output from these two multiplexers will be fed into another multiplexer, and that is what gives us the final output. So let's have a look at how that works. So we have two 2 cross 1 muxes, and another 2 cross 1. So the the first two multiplexers here, they have a single select line, and the second one has a different select line, which is S1. Okay, so we know that a 4 cross 1 mux has 4 inputs. So among these 4 inputs, I0 and I1 are fed into the first multiplexer, and I1 I2 and I3 are fed into the second multiplexer. So let's to know exactly how it works, let's see. So first let's take S1 as 0 and S0 also as 0. So if S1 is 0, that means we need, I mentioned while talking about a 2 cross 1 mux that if S1 is 0, then the first input will be taken, and if S1 is 1, then the second input will be taken. So since S1 is 0, it will take the input that comes from the upper 2 cross 1 mux and ignore the input that comes from the second 2 cross 1 mux. So since our S1 is 0, we'll just look at the input from the first 2 cross 1 mux. And then we have that S0 is also 0. So if S0 is 0, that means we are talking about this multiplexer, and since S0 is 0, it will take the first input to this multiplexer, which is I0. So this I0 will be the output of the first multiplexer, and since the third multiplexer only takes in inputs from the first multiplexer, the output comes out to be I0. Similarly, if you have 0 and 1, so that since S1 is still 0, it takes input from the first multiplexer. So while taking input from the first multiplexer, if S0 is 1, so 1 means it takes the second input, which is I1. So I1 is the output of this 2 cross 1 mux, and the I1 is what is the first input of the third 2 cross 1 mux, which it displays as the output. So this means it's I1. Now if S1 is 1, that means now the multiplexer takes inputs from the mux on the bottom here, the 2 cross 1 mux on the bottom, and S0 is 0. So now S0, like I mentioned, acts as a select line for both the above and below multiplexers. So since the select line S0 has a value of 0, the first input line will be selected, which means I2 gets selected, and I2 is the output from this mux. And since S1 is 1, the input from the bottom mux is the only input that is considered and is directly taken as the output. So I2 is the output. And similarly, if you have 1 and 1, it means the bottom mux is chosen. And since S0 is 1, I3 is taken as output from here. And that directly comes out as the output from here. So like you can see, this is the same as the 4 cross, how the 4 cross mux, 4 cross 1 mux was implemented. And we can successfully implement that using a 2 cross 1 mux. So now uh, let us look at a little more complicated circuit, which is 8 cross 1 mux using 2 cross 1 mux. So again, the first thing that we have to do is find out how many multiplexers, how many 2 cross 1 multiplexers are actually needed to implement this. So we divide 8 by 4, 8 by 2, that gives us 4, then 4 by 2, that gives us 2, and then 2 by 2, that gives us 1. So first we need 4 2 cross 1 multipliers, then 2 cross 1 2 multipliers, and finally uh, 1 2 cross 1 multipliers. So basically we have 4 in the first level, 2 in the second level, and then 1 here, and the output comes out from here. So this is how so we have one select line for each level. So this is S0, this is S1. S1 acts as the select line for both these multipliers. And here we have S2 that acts as the select line for all the multipliers at this level. Uh, I think I made a mistake. So the order should always be S0 will be the select line for this, and S2 will be the select line for this. So we should always have the highest preference to the multiplexer which is placed at the end. So that should be something which is kept in mind always. Then we have 8 inputs here: I0, I1, I2, I3, I4, I5, I6, I7. So we have 8 inputs, and let's implement the 8 cross 1 mux here. So we have S1, S0, S1, S2, S1, and S0, and let's see the output. So first we have 0, 0, and 0. So if S2 is 0, it means the 2 cross 1 mux takes the input which is on top, right? So it means it's taking the input from this particular mux. Uh, so S1 is also 0, which means this multiplexer is also taking the input from the mux on top alone. So it's taking an input from the first multiplexer which we have taken. And since S0 is 0, that means I0 is the output of this multiplexer. So I0 is taken as output here, and I0 is the input to S1. And like I mentioned, the first input will be taken. So I0 is the output from S12. And S2 selects I0 as the input again. So our output comes out to be I0. So similarly, for let's just take a random value of, let's take a random value here, 0, 0, 1, 0, 1, 0. Okay, let's take this example, 1, 0, 0. So if S2, if the value of S2 is 1, that means it's this select line is what, this select line will be chosen as, this input line will be chosen as the output by S2. So then we look at this particular mux. Here we have S1 as 0. So it takes input from this particular mux, and S0 is again 0. So the upper input line in this multiplexer will be taken, which is I4. So for this particular case, we have I4 as the output line. Similarly, for we can write the truth table for all the possible values. 101 gives us I5, 110 is I7. Right, so this is how you implement 8 cross 1 using a 2 cross 1 mux. So now let us talk about implementation of boolean functions using a multiplexer. So what this does is it reduces the need for multiple gates. You can just implement the entire given boolean expression with just one device, which is the multiplexer. So this is really helpful in while actually building circuits in real life as well. So let's talk about how we can implement a three variable boolean expression using 4 cross 1 as well as 8 cross 1, and then we'll talk about how we can implement a 4 variable expression using 4 cross 1 and 8 cross 1 as well. So let's say we have fun function of a, b, c is equal to summation of minterms of 1, comma 2, comma 4, comma 5. Okay, so in a 4 cross 1 mux, we know that two we have two in select lines. So out of these three variables, two of them are chosen in the select lines, and the third one is fed in some form or the other through the various input lines that we have. So the first step that we need to do is we need to take a KMAP. Here you have C dash and C, A dash, B dash, A dash, B, A, B, and A, B dash. So this is 1. We have 2 as well. Okay. Yeah, so the what we actually do here is we don't group any of the elements in the K-map. We try to look for what is actually taken as the output for each term of A and B. So let me just use the demarc side by side. So 4 cross 1, no, sorry, the mux. 4 cross 1 mux, as we know, has 4 inputs and 2 select lines, which we have taken as A and B, right? So let's see for different values of A and B, what is actually getting chosen as the output. So we know that if we have A and B as 0, the first input line is what gets chosen. So for A complement, B complement, we can see that the first we can see for A complement, B complement, we have the value as C alone, right? So we just look at this particular row of A complement, B complement, and the output is only in C. So we know basically what we are finding here is that whenever you have A complement, B complement, what gets chosen as the output here is C. So we know that in a mux, the first input gets chosen whenever you have 0, 0 as the select lines. So C is fed as the first input. Then we talk about 0 and 1, which is A complement B. So like you can see here, you have C complement plus C, which is basically 1, right? So 1 is the second input. So if you have A complement B, the output that you will get is 1. Then for AB, no, the third one we'll actually look at is 1, 0. So for 1, 0, we know the third select line gets chosen, which is 1, 0 is A, B complement. So for A, B complement, you can see the output is prevalent only for C complement. So the third input line will be C complement. And for AB, like you can see, it's just 0 in both the columns. So this will be 0. So similarly here we can see that depending on the values of A and B, we we can find what is the input line that needs to be selected, and that will be displayed as the output. So that was using 4 cross 1 mux. So now when we are implementing a 3 variable system using 8 cross 1 mux, uh, yeah. So because when we are implementing it using 8 cross 1 mux, we already have 3 select lines. So all the 3 variables A, B and C will be taken as input here. The only thing that will be needed in our input lines are 0 and 1. So for A complement, B complement, C, we know that the first input line will get chosen, which is 0 here. And then for A complement, B complement C, we can see that it's 1. So the second input line will be 1. Then we will have 0, 0, 0 is done, 0, 0, 1. Then we have 0, 1, 0, which is A complement, B and C complement. So A complement, B and C complement is again 1. So this is 1, 2. Then we'll see A complement, B, C. So A complement, B, C is again 1. So this input is 1, 2. Then we have 1, 0, 0, which is A, B complement, C complement. So A, B complement, C complement is again 1. So like you can see, the rest of them are all zeros. Let us just write it down. Right. So this is how we implement a 3 variable system using 8 cross 1 mux. So since all the 3 variables are used as select lines, the only inputs are 0 and 1. So now let us look at how we can implement 4 variable boolean expressions using both 4 cross 1 and 8 cross 1. So see, here we had 3 variables. So in 4 cross 1, we took 2 as input, 2 in select lines, and the third one as one of the input lines. and we took all three as select lines in the 8 cross 1 and just zeros and ones in the input line. So for 4 variable, what we do is the 8 cross 1 will have 3 select lines and 1 as the input. I mean, the fourth variable as input. And in 4 cross 1, we'll have 2 select lines. And C and D will actually be passed through some external gates and then fed as input to the 4 cross 1 mux. So let's take an example here. So let the example be f of a, b, c, d is written as summation of minterms 0, 1, 5, 7, 8, 9, 13, and 15. Okay, so for this, first let's make the KMAP. So let this be A complement, B complement, A B, and A B complement. This is okay. So this is 0. This is 1. This is the fifth, 7, 8, 9. Then we have 13 and 50. Right. So now simultaneously let's take an 8 cross 1 mux with inputs A, B, and C. Right. So now we have 8 input lines. Okay, so now let's see what our input will be for each part, each possible combination of the select lines. So the first combination that we take is obviously 0, 0, 0, which means A complement, B complement, and C complement. So A complement, B complement, C complement is these two rows here, and like you can see, both the result for A complement, B complement, C complement is D complement plus D, which is 1, right? So the first input that is fed here is 1. So next we see A complement, B complement, and C. So this is A complement, B complement, and C is these two rows here. Like you can see, they both of the uh, boxes here have 0. So the input here will be 0. Next we see for A complement, B, C complement, which is these two. So like you can see here, the output is present only for D. So the input here is D. Then we see for A complement, we have seen up to A complement, B, C complement. So now let's see for A complement, B, C. So again you have D here, A complement, B, C is these two uh, boxes, which is D again, is D. So after that we have 1, 0, 0, which is A, B complement, C complement. So A, B complement, C complement again gives us 1. Then we see A, B complement, C, which is these two, and we get 0 here. Then we have A, B, and C complement. A, B, and C complement is these two boxes, which is giving us only D. So the input for the seventh one is D. And lastly, we have ABC, and we again get D as the input here. So this is 8 cross 1 mux for for this particular four variable function. I mean the four variable boolean expression. So now let us try and implement the same one using 4 cross 1 mux. So in 4 cross 1 mux, what we have is we just have two select lines, right? So let me just make the multiplexer here. I have A and I have B, and I have four different expressions here. So let's see for the different values of select lines, what are the actual values of inputs that we'll be taking. This is a 4 cross 8 cross 1. Okay, so for 0 and 0, which is A complement B complement, I get the output as C complement D complement plus C complement D, which is basically just C complement. Then for A complement B, I have C complement D plus CD, which is just D. So D is the second input. Then for A B complement, I have C complement again, and for A B 1 and 1, I have C complement D plus CD complement, which is again D. So this is taken as D. So like you can see, there are two different variables which are being taken as an input here. But in an 8 cross 1, the third variable has actually been taken as a select line. So we just need to give one input from these input lines. So this is how you can implement a boolean expression using mux. So let's see a few more questions here, just so you are familiar with this idea. Okay, so let's take this question. F of A comma B comma is equal to summation of M 3 comma 5 comma 5 6 7 9 10 12 and 15. Okay, so we have to implement this using a 4 cross 1 box, right? And since we are taking two input, since we are implementing a four variable expression using a 4 cross 1 mux, we are taking two inputs as we'll be taking two different inputs, I mean, two different variables in the input lines. So, see, in this particular example, we never had to perform operations between these variables while taking them as input lines because we directly got C complement and D. But whenever there is a particular operation needed, like, if we had one zeros, if we needed any different operations here, like 1001, and we had to perform C plus D complement and things like that, then we'll have to use external gates like an AND gate or an OR gate to actually simplify it fully. So this is using 4 cross 1 mux and external gates. So first let's make the KMAP. Okay, so this is okay. So now let's see what are the possibilities here. So now we have 3 as the first one. So this is 0, 1, 2, and 3. We have 1 here. Then we have 5, 5, 6, 7, 9, 10, 10, 12, and then 5. So now let's see. This gives us, this is A and B, and we have the 4 cross 1 marks. We have 4 inputs. Okay, so let's see for different values of the select lines what we have to take as the input. So we have 0 and 0, which is A complement, B complement. So for A complement, B complement, you can see that the only output that you're getting is CD, right? All the other places you have 0. So that is the first select line that we'll have to take, CD. And then we have 0, 1, which is A complement into B. So for A complement into B, you have C complement D plus CD plus CD complement. Right. So here let's see. We have, let's take D common here, and you will get C plus C complement plus CD complement. So we know that C plus C complement is 1. So we can just write this as D plus CD complement. And we also have an expression that x plus x dash y gives us x plus y. So we can simplify this as, we can just write this as d plus c. So the output for this is just c plus d for a complement b, right? So then we have a b, no, then we have a b complement, which is 1 0. See, while writing this, you have to make sure that you take the third input from the last row of the KMAP. Okay, because 1 0 selects the third line and 1 1 selects the last line. So, but in the KMAP, however, the third input is the last row. So we have to ensure that we always take the correct input. So 1 0 means A B complement. So for A B complement, we have C complement T plus C D complement, which is basically C XOR of D. Right. So here we have C XOR D. And then for AB, which is 1 and 1, we are taking the third row, which is C complement D complement plus CD. And this is the expression for XNOR. Right. So we have C XNOR of D. Right. So these are the 4 inputs that actually need to be fed into the select lines. So now let's see. We have C and D here. First, we need to pass them through an AND gate. That gives us CD, and we'll pass this. Let's make this 4 cross 1 box again. This is A, this is B, this is the output. So this is the first input line. Then we need to take C and D, and then it's passed through an OR gate. This is the second input. Then we have C XOR D. No, this is XNOR. So C XNOR D is the third input. And then the final input is C XOR of D. So this is how you can implement a 4 variable expression using a 4 cross 1 box. So 2 of these inputs will be select lines. You can take any 2 inputs as select lines and any 2 inputs as the input lines. And depending on what operation needs to be performed, you will have to use logic gates to get that particular expression and then take select that as one of the input lines. So that is implementation of a four variable expression using 4 cross 1 mux. Just a second. Okay, so that was about multiplexers. So now let's look at the exact opposite, which is demux or demultiplexers. So in mux you had two select lines, four inputs and one output. So here it's the exact opposite where you have one input, two select lines and four outputs. So this is called a 1:4 demux. Okay, so what mux did was it selected one particular output from many input lines. So among the many input lines you had, these select lines used to pick just one of them and display them as the output. So a demux does the exact opposite, which is why it's called a data distributor. And the mux was called a data selector. Right. So for demux, let's say we have a 1 cross 4 demux and you have I here. This is S1 and S0. Right. So if S1 and S0 are 0 and 0, the input comes out from the last select line and the others all get 0. Then if we have 0 and 1, this is the, this gets the input. The output comes out from the second input line alone and the others get 0 as the output. Similarly, 1 0 gives the output I from the third output line and the others get 0 as the output, and similarly for 1 1 the output is from the last select line. So this is a 1:4 demux, and similarly you also have a 1:2 a 1:8 demux, and the number of select lines here is 1 and this is 3. So the number of select lines are the same as we had in the mux. The only thing that changes is the number of inputs that you had in the mux becomes the number of outputs that you have in demux. So one of the main uses of let's see how we can implement a combinational circuit like full subtractor using a demux. So like you saw sometime back, the full subtractor had a lot of logic gates which were necessary. You needed multiple XOR gates, multiple OR gates, and multiple AND gates and an OR gate, right? So actually, when you're actually making circuits in real life, such a huge amount of gates gets quite tedious to implement. So that is the main function of mux and demux. Like you can see here, you just needed one mux to implement a huge boolean expression, which would otherwise need a lot of and or and not gates to implement. So similarly, let's see how something like a full subtractor can be simplified using a demux. Right. So the truth table for a full subtractor was this was A, B, C. We had a difference and a borrow out. So I'm not explaining the truth table again because we just did that some time back. This was 0, 0, 0 and 0, 1 and 1, 0, 1, 0, once again 1 and 1, 0, 1, 1, 0 and 1. So 1, 0, right? So what we can do is we can write this as a product of minterms, right? So D gives us 1 for values 1, 2, 4, and 7, right? So D is 1, 2, 4, and 7. And borrow out is summation of minterms of 1, 2, 3, and 8. I mean 3 and 7. Sorry. So 1, 2, 3, and 7. Right. So in a demarks, what you actually get as the output are. So wait, just a second. Okay, yeah. So in a demarks, let's take 1 is to 8 demarks, where you have A, B, and B naught as the A, B, and C as the select lines. So for us to get 1 here, so the input here will be 1, right? So the input is 1. So if we have the particular values like, so basically we need to get it such that when we get 1 in a particular input line, which gets selected for the corresponding value of ABC. So like let's say ABC is equal to 0. So if we have 0, 0, and 0, right? So in that case, the first select line gets selected, but we do not want the value of 1 for 0, right? We want the value of 1 for 0, 0, 1. We want the value of 1 to come out for 0, 1, 0, and so on, only for particular values, right? So we want the value of 1 to come out for 1, 2, 4, and 7. So we take 1, 2, 4, less, okay, and 7. And what we do is all of these are passed through an OR gate. And this is the difference. So basically, for any of these values, 1, 2, 4, or 7, if any of these select lines get selected, they will have 1 as the output. And as long as 1 is being passed through an OR gate, the other values don't matter. So then the difference comes out as 1, right? So similarly, for borrow, we need to take 1, 2, and then 3. And these three are passed through an OR gate similarly. And this gives us the borrow. Wait, sorry, not 2. So we need to, not 2, it's 1, 3, and 7, right? So the seventh one is 1, 2, 3, and 7. Okay, so the seventh one is taken through the OR gate as well. Let me just make this a little better. So this was the demarks. We had 1, 2, 3, 4, 5, 6, 7, and 8 outputs. So we had to take the first one, the second one, the fourth one, and the seventh one for difference. This was D. And then we have 1, 2, 3, and 7 for borrow. Right. So this is how we've used a 1 is to 8 demarks for subtractor, where A, B, and C are used as the input line. So like you can see, the circuit has become much simpler, where you've just used 1 demarks and 2 OR gates. So that is the application of demarks. So with that, we've come to an end of multiplexer and demultiplexer. So let's have a look at the next topic, which is encoder and decoder. So these have similar applications to multiplexer and demultiplexer too. What an encoder does is it minimizes the number of data lines that are needed to transmit the same information that are being transmitted through a larger number of data lines. So if you are given n inputs into an, if you give n inputs, if you give, yeah, if you give n inputs to an encoder, it gives out m outputs, and the number of inputs is usually equal to 2 to the power m, the number of outputs. So encoders are of the type 2 is to 1, 4 is to 2, or 8 is to 3. So what a decoder does is whatever is received, whatever after the encoder minimizes the number of data lines and the data is transmitted, the decoder again distributes the data and finds out all the possible outputs that were there. So let's say you are transmitting x dash y dash, x dash y, x y dash, and x y to an encoder, a 4 is to 2 encoder. So see, we just need two lines to transmit this, which are x and y. So the encoder has reduced the number of lines from 4 to 2. We just need these two lines to transmit the data. So then after this data is transmitted, the decoder gets these two inputs, x and y, and then it writes all the four possible uh, outputs here, which are x dash y dash, x dash y, x y dash, and xy. So this is a 2 is to 4 decoder, right? So a decoder can be used to, let's have a look at one of the applications of a decoder, which is uh, implementing a full adder. Okay, so for that, the truth table of a full adder looks something like this: A, B, C, sum and carry out, 0, 0, 0, 1, 1 and 0, and for 0, 1, 1, 1, 1. So this is the truth table for a full adder, right? So here we can see that the sum is 1 when we have 1, 2, 4, and 7. Right? So sum can be written as summation in terms of 1, 2, 4, and 7. And difference is 1 when we have 1, 2, 3, 5, 6, and 7. So I mentioned that when you give x and y as the inputs to a decoder, the outputs it gives are x dash y dash, x dash y, x y dash, and x y. So similarly, if you are giving three inputs to a 3 is to 8 decoder, let's say the inputs are A, B, and C, right? So it gives us 8 outputs, which are A dash, B dash, C dash, A dash, B dash, C, and so on. So these are the, okay, so these are the 8 outputs. So the first one is A dash, B dash, C, then it's A dash, B dash, sorry, the first one is A dash B dash C dash, then we have A dash B dash C, and so on. We have 8 inputs. So we know that for sum, we have to take the first, the second, the fourth, and the seventh ones. Okay, so we have to take these four and then pass them through an OR gate. And then similarly for carry, we have to take the third one, the fifth one, the sixth one, and the seventh one, and then pass them through an OR gate. Right? Because see, the second one here is basically A complement, B complement, C. Uh, so if let's say for A complement, B complement, C, we got the sum as 1, right? So in case the output here is 1, and so that makes the other outputs here irrelevant. So if any of 1, 2, 4, or 7 are coming out to be 1, the output from this particular OR gate also comes out to be 1. So that tells us that these four, amongst these four, any of them are 1 for the difference to be 1. So that is the output for our difference. And for carry out, it's the summation of 3, 5, 6, and 7. So this is implementation of full adder using a decoder. And similarly, you can also simplify Boolean expressions using a decoder. However, that's not important for us. You can try implementing the ones we did using MUPs using decoder just for a better understanding if you have time. So let's see a few encoders which are important for us. What these encoders do is they change data from one type to another. So we'll primarily look at two things. The first one is binary to gray, and the second one being BCD, that is binary coded decimal to XS3. Right. So first thing that we need to know is how do we actually write these numbers in the particular form that we're going to change it to. Okay, so let's talk about gray code first. Okay, let's see how we can write binary numbers in gray and similarly gray numbers which are written in gray code in binary. So let's take an example 0 0 0 1 1. Okay, so the first thing that we need to know is the number of digits remains the same in gray code as well. So if it's a 3-digit binary number, we'll get a 3-digit gray coded number. And the first number is called the most significant digit. And the most significant digit always remains the same in binary and gray. So we write the 0 as it is. So then what we do is we compare the first two digits, right, which are 0 and 1. So if the two digits that we're comparing are the same, then we write 0. And if the two digits that we're comparing are different, we write 1. So since 0 and 1 are different, we write 1 here. Then we compare the next two digits. Since 1 and 1 are the same, our output will be 0. So this extends to numbers of any length. So let's take 1, 0, 1, 0, 1, 1. So this is a 6-digit number. So the output will be 6 digits as well. So like I mentioned, the most significant digit remains the same in binary and gray. So we have 1 here. Then we start comparing two digits at a time. So since 1 and 0 are different, that means our output is 1. Then we compare the next two, which is 0 and 1. Since they're again different, we get 1. Then we compare this 1 and this 0. Again different, so the output is 1. Then 0 and 1 is again different, so the output is 1. 1 and 1 are the same, which gives us the output 0. So this is the binary number, and in gray code, this is how it's written. So let's take one last example: 101 011 01. Okay, so the most significant digit here is 1. So comparing the first two digits, 1 and 0, they are different. So we write 1. Then 0 and 1 are again different. So we write 1. Then this 1 and the next 0 again different. So 1. So comparing this 0 and 1 again different. So 1. 1 and 1 are the same. So we write 0. 1 and 0 again different. So 1. 0 and 1 again different. So 1. So this is the binary number, and this is the gray coded number. So now let's see how we can convert gray to binary. So let's say we are given 1 1 0, and this is in gray code. So again, like I mentioned, since the most significant digit always remains the same, and the number of digits also remains the same. So the first digit being the most significant one, that remains 1 in binary as well. So now what we need to do is we need to compare the first digit that we have written here with the second digit of gray code. So when you're converting gray to binary, always write it below the gray code. So first what we do is we compare 1 and the second digit here. Then we compare the second digit here with the third digit here, and so on and cross. So 1 and 1 are the same, right? So we write 0, and then 0 and 0 are again the same. So we write 0 again. So this is the binary equivalent of 110 in gray. Now if we have, let's take another example, 110 in gray. So the most significant digit remains the same. Then 1 and 1 are the same. So we write 0. So no, wait, I've written the same number again. Okay, I'm sorry. Let's take a different number, which is let's take 111. So here 1 is the most significant digit, that remains the same. Then 1 and 1 are the same, so we write 0. And then 0 and 1 are different, so we write 1. So that is the binary equivalent of 111 in gray. So now the last example, let's take a larger number, 110010, and this is in gray code. So let's convert this to binary. So the most significant digit remains the same, which is 1. So 1 and 1 gives us 0. 0 and 0 is again the same, so 0. And then 0 and 0 again same, so 0. 0 and 1 are different, so we write 1 here. And then 1 and 0 are different, so again 1 here. So this is the binary equivalent of the above mentioned number in gray code, right? So now let's see how we can draw a logical circuit using all the logic gates that we know to simplify a binary code to gray code, right? So let's take a 4-bit number, all right, and here we have G0, G1, G2, and G3. Like I mentioned, the number of digits will always be the same in binary and gray, so we don't have to worry about that. So let's take 0, 0, 0, and 0 here. That gives us 0, 0, 0, 0 in gray as well. Now if we are taking 0, 0, 0, and 1, right? So the most significant digit remains the same. Then 0 and 0 are 0 because they are the same. Then 0 and 0 are again the same, so we write 0. 0 and 1 are again are different, so we write 1. Now we have 0, 0, 1, 0. So the most significant digit remains the same. Then 0 and 0, comparing them, they are the same, so we write 0. 0 and 1 are different, so we write 1. Then 1 and 0 are again different, so we write 1. The next number is 0, 0, 1, 1. So 0 is the most significant digit. Then 0 and 0 are the same, so we write 0. 0 and 1 are different, so we write 1. 1 and 1 are the same, so we write 0 here. Okay, so similarly we go on writing this for all 16 inputs. So we have 0, 0, 0, 1, 0, 0. For this it will be 0, 1, 1, 0, 0, 1, 0, 1. This gives us 0, 1, 1, 1. Then we have 0, 1, 1, 0. So this we get 0, 1, 0, 1. Then we have 0, 1, 1, 1. For which we get 0, 1, 0, 3. And then, so we have to write this for all 16 possible values of B and the corresponding values of G as well. Right. So after writing that, what we have to do is we write. So after writing that, I know it's an exhausting process, but the exam actually requires you to write all 16 of them and then find the value of G3, G2, G1 and G0 separately, right? So after writing all of them, you have to find out the summation of minterms of each of them and then use a KMAP to simplify the whole thing, right? So So what we get, we need, let's see how it's done one at a time. Okay, so I just want all of you to write this all the way up to 16 terms on your own and then just compare it with this. Okay, so for G3, let's take a K-map. Here you have B2 and B1 and B0, and here you have B2, B3. Okay, so we have take it here, B2, B3 dash, B2 dash, B3, B2, B3, and B2. Okay, this is B1, B0 dash, B1 dash, B0, B0 dash. Okay, so upon drawing this entire truth table, wait, yeah, we should actually write B3, B2, B1, and B0. This is B3, B1, and B0. So upon calculating the entire thing, like you can see, G3 will not become 1 until the value of B3 gets to 1. And we also know, so only when B3 is 1, you get the value of, only when B3 is 1, you get the value of G3 as 1. So this is 1, 1, 1, and 1. Right? So from this, we can, upon simplifying the K-map, you will simply get B3. So you get G3 is equal to B3. And we also know that the most significant digit always remains the same. So if G3 is 0, that means B3 was obviously 0. So that is for G3. So for G2, upon we draw the same K-map again for G2, the 4:4 K-map. So here we get, I mean, if you have drawn the entire 16, if you have written the entire 16, all the 16 terms here, then it will be possible to match with this. So here we get 1, 1, 1. This will be B3, B2, B3 complement B2 and B3, B2 and I've written this as B1, B0 dash, B1 dash B0, B1, B0, B1, B0 dash. So you get ones here, and so you get G2 as this is B2, B3 complement B2, and you have ones in B3, B2 complement. So like you can see, this is an XOR gate. So we have B3 complement of B2. So similarly, what we do is we write the entire code, then we see all the minterms of the particular digit, like we did for G3 and G2, and then you make the K-map and find each of the terms. So similarly, upon calculating, we'll get G1 as B2 XOR of B1 and G0 as B1 XOR of BO, right? So finally, how we present the answer is we have B3, B2, B1 and B0. So B3 directly gives us G3, and then we have B3 XOR of B2 giving us G2, B1 XOR of B2 is G1, and then B1 XOR of B0 is G0. So that is this is the logic circuit that we wanted that converts binary to gray code. So now let's look at the second one that we wanted, which is binary coded decimal to XS3. Okay, so XS3 code is a much simpler one to write when compared to gray code. So the only difference is XS3 code always starts from 0, 0, 1, 1. So whatever is the binary number in BCD, all you need to do is you need to add 3 and it will give you the XS3 code. So let's say we have 0, 0, 0, 1. So this is the representation for 1, right? So how do we represent 3 in BCD is we need to add 3 to this, which gives us 4. So 4 is written in binary as 0, 1, 0, 0. So this is the XS3 code for 0, 0, 0, 1. Whatever number you have, you just need to add 3 to it and write it in binary. So 0, 0, 0, 0 gives us 0, 0, 1, 1. 0, 0, 0, 1 gives us 0, 1, 0, 0, and so on. So that is BCD to XS3. So now let's see how we can write the code for it. So we have a 4-bit binary code again, B3, B2, B1, and B0. And we have XS3 4 digits as well, E3, E2, E1, and E0. We have 0, 0, 0, 1. This is 0, 0, 1, 1. For 0, 0, 0, 1, we get 0 1 0 0. So like you can see, you just need to add 3 to the particular binary digit and then convert it into binary again, and that will give you the excess 3 code. 0 1 1 0. 0 1 0 0 4 0 1 1. Yeah, 5 1 is 1. Okay, so this is the binary equivalent of the decimal number 9, right? So we stop at this because we are talking about binary coded decimals alone. So decimal numbers range from 0 to 9. So we are on after this, the entire table would be just a don't care condition because it doesn't matter after this point because we are not going to get any binary coded decimal for decimal numbers higher than 9. So everything below this is a don't care. So now let's try and let's calculate E3 using a KMAP. Okay, so here we have P1, P0 complement, P0, P1, P0. Here we have P3. Okay, so we are calculating for E3, right? So E3 was 1 from 0, 1, 2, 3, 4. So from 5 onwards, E3 was 1. So from for 5, 6, 7, 5, 6, 7, 8, 9, the values of E3 was 1, right? So on this K map, we need to write 1 in these places, 8 and 9, right? And we also know that from 10 to 16, the value for BCD is don't care. So we need to add the don't care condition to all these boxes in the KMAP as well, right? So what a don't care condition does is it's just included if it helps us simplify the KMAP, or else we do not consider that particular box. So now let us group these. We can see a 4 map here, another 4 map here, then a 4 map here, and then this 4 as well. So we have 3 different mappings. So oh wait, we can include this entire 8. So this is a 8 map. We have one group of 8 and 2 groups of 4. So the last 2 rows, the only thing that we have in common is B3. So we have B3. Then we have this 4 map, which is B0 and B2. So we have B0, B2. And the last grouping that we had was this 4 map over here, which is B1, B2. Right? So this is B1, B2. Okay, so this is the final expression for E3. So similarly, we can calculate for E2 as well, where we make the same KMAP. So here we have, for E2 we have ones in 1, 2, 3, 4 and 9. Right. So E2's 1, 2, 3, 4 and 9. And all of these are don't cares, not this one. This is 8. So these are all don't care conditions because anything greater than 9, like I mentioned, is a don't care. So now upon grouping, let's take these 4, then we have these 2 and these 4. So that this 4 grouping gives us B2 complement into B0. The second grouping of 4 gives us B1, B2 complement, and this one grouping of 2 that we have gives us B2, B1 complement, B0 complement. Okay, so that is for E2, and similarly we can write for E1 and E0. So I will just write the answer here so that you can check it later. Just do it yourself and check it with the final answer here. So E1 is given by B1 complement B0 complement plus B1 B0, which is basically B1 XNOR of B0, and E0 is just given by B0 complement. Okay, so that is about these converters, these encoders that we have. Okay, just give me a minute. Okay, the last type of encoder that we have is called a priority encoder. So, like I mentioned, an encoder has m outputs and 2 to the power m inputs. So let's take the example of a 4 is to 2 encoder where we are given 4 inputs and 2 outputs, I0, I1, I2 and I3. And the outputs, let's say they are Y1 and Y0. Okay, so basically what we need to know is the priority of each of these inputs goes from lower to higher as we go down. So I0 has the least priority and I3 has the highest priority. So let's make the truth table for this. Let's say we have I3, I2, I1 and I0, and we have Y1 and Y0. So if all of them are 0, then we don't care about these values. They do not exist. So then if we have 0, 0, 0 and 1, right, then both of these values are 0. So then if we have 0, 0 and this is 1, right? So I1 has a higher priority than I0. So if we have I1 as 1, then the value of I0 doesn't matter because the higher priority is being given to 1. So we have I0 as a don't care condition, and this comes 0, 1. And then similarly, if we have 0, 1 here, if we have 1 and I2, then we don't care about the next few values of I1 and I0 as well. This gives us 1, 0. Then if I3 is 1, we don't care about the values of I2, I1 or I0. And in that case, Y1 and Y0 both give us 1. Right? So now we got the output here. So let's use a truth table, and let's use a KMAP and actually find out how Y is related to the inputs. So this is the truth table that we have. Let's make the KMAP where you have I0, I1, I2 and I3. I1, I0. This is I3, I2, I3, I2, I2. Okay, so we are doing this for Y1. So for Y1, we had for whenever I2 became 1, all the values of I1 are 1. So regardless of what value of I1 and I0 we take, the value of Y1 will always be 1 if I2 is 1. So so for any value of I2 which is 1, right? We have 1 here. And obviously if I3 is 1, in that case too Y1 is 1 because again you don't have to care about the upcoming values. So for any value of I3 which is 1 as well, you have 1 here, right? So you group this 8 and you group this 8. So this gives us, this is I2 and this is I3. So you get I3 plus I2, that is the value of Y1. So similarly for Y0, if you make the same KMAP, so Y0 is 0 even when the value of I2 is 1. So we can't just write ones for I2. However, we know that if I3 is 1, then Y0 is definitely 1. And for I2 being 0 and I1 being 1, we have Y0 is 1 again. So first thing that we'll make sure is wherever I3 is 1, uh, there Y0 is definitely 1. So these are the 8 places. And then when I2 is 0 and I1 is 1, then uh, again Y0 is 1. So I2 being 0 is this place, and I1, which is I1 being 1 is, so these are the two cases. So let's take this 8 group and then this 4 group, these two and these two, right? So this 8 whole group gives us I3, and this group of 4 here gives us which is I1 common and I2 dash, right? Okay, so plus I1 I2 dash. So this is the value of y0. Right, so this is how you make a 4 is to 2 priority encoder. You can try making the same for 8 is to 3 or 2 is to 1. So that with that, we have come to an end of encoders. We have only one topic left, which is the parity generator and parity checker. So first, let's talk about parity generator. So we have two types of parity, even and odd. Okay, so for even parity, if we have even number of zeros, even number of ones gives us 0, and odd number of ones gives us 1. Okay, so let's say you have A, B, and then the parity generator. Let's denote it by PE for even parity. So here you have 0 ones, which is an even number, that is 0. 0, 1. Here you have an odd number of ones, right? So we get 1. Again, an odd number of ones, so 1, and 2 ones, which is even, so we get 0 as the output. So, like you can see, this is the truth table of an XOR gate. So, P E can be written as A XOR B. Okay, so now let's see the same parity generator for A, B, C, three variables. So we have 0, 0, 0, 0, 0, 1. So this remains 0 because even number of ones. Here you have odd number of ones. 0, 1, 0, again odd number of ones. 0, 1, 1 gives us 0, 0, 1, 0, 0, again 1, 1, 0, 1 is 0, 1, 1, 0 is 0, and 1, 1, 1 is 1. So whenever you have even number of ones, you put 0 here, and whenever you have odd number of ones, you put 1. Right. So now let's find the expression for this by drawing a truth table. So here you have B complement, C complement, B complement, C, B, C, B, C complement, this is A complement and A. So for this, we have A complement, for A complement, B complement, C, we have 0. Or let's just take the ones. So for A complement, B complement, C, we have A complement, B complement, C, this is 1. Then we have 1 for A complement, B, C complement, which is with A complement, B, C complement. Okay, so this is 1. Then we have 1 for A, B complement, C complement, and then 1 for A, B, C. Right. So, like I mentioned before, this is a chessboard configuration. So, a chessboard configuration means A XOR B XOR C. Right. So, this is the same as the sum of a full adder. So, that is how an even parity generator is expressed for three variables. So the next thing is odd parity. So in odd parity, what you have is if there are even number of ones, you denote it with 1, and odd number of ones are denoted with 0. Right. So now Now the truth table of for this will be the exact opposite, right? You have one for A complement B complement C. You have one for A complement B C. You have a one in A B complement C and A B C complement. Okay, so this is not the desired chessboard configuration that we want. So let's try and simplify this using just the laws of Boolean algebra that we know. Right, so we have A complement B complement C complement plus A complement BC plus A B complement C plus A B C complement. So from this, let's take A complement common, right? So we have B complement C complement plus BC, and from here again, if I take A common, I get B complement C plus BC complement. So this is the XNOR gate for BC. So I get A complement XOR C complement, which is the symbol for XNOR, and here I have A, and B complement C plus BC complement is B XOR C, right? So this entire expression is actually of the form A complement. Let's take B XOR C as a new variable D. So this is A complement D complement plus AD, right? So this form is of the form A XNOR D. So if we can write this entire expression as A XNOR of B XOR C. So this is the full expression for odd parity, and for even parity it was just A XOR B XOR C. Okay, so that is about parity checker. I mean, that was about parity generator. So the last topic is parity checker. And in parity checker, you just have to write the truth table for this parity. This is parity generator, and here we have a parity checker. Okay, so if you have 0, 0, 0, so here what you do is you write uh, for every input that you're taking, like here you're taking 0, 0, 0 as the input, you write 0 and 1 both in the parity generator. And then for 0, 0, 1, you write 0 and 1 again. Then for 0, 1, 0, you again write 0 and 1. And then for 0, 1, 1, again 0 and 1. Then for 1, 0, 0, you again write 0, 1, 1, 0, 1, 0, 1, and here 1, 1, 0, 0, 1, and for 1, 1, 1, you write 0 and 1, right? So what you do is we know that for 0, 0 and 0, the value of even parity is going to be 0, right? So corresponding to the 0, to affirm that it's actually correct, we write 0. So to the value which is actually correct, we write 0 in the checker, and to the value that is wrong, we write 1. So we know that for 0, 0, 0, we have an even number of ones. So our parity, we are talking about even parity here. So our parity generator should actually give us 0. So the parity checker confirms that 0 is correct and 1 is wrong. So for 0, 0, 1, we have an odd number of uh, ones. So our output in the parity generator should be 1, which means 0 is wrong. So to write wrong, we write 1. So here 0 basically means correct and 1 means wrong. So corresponding to the 0 we write 1, and corresponding to the 1 we write 0 because that is the correct value. So again here you have an even number of, I mean you have an odd number of ones. So 0 is wrong and 1 is correct. So here you have you have an even number of ones. So 0 is correct and 1 is wrong. Here again, odd number of ones. So 0 is wrong and 1 is correct. Here, odd number of even number of ones. So 0 is correct and 1 is wrong. Even number of ones means 0 is correct, 1 is wrong. Odd number of ones means 0 is wrong and 1 is correct. Right, so this is the entire code for parity generator. Parity checker. So to check, to find the output of parity checker, let's take the, now we'll have to take a four variable truth table along the fourth variable being the parity generator. Okay, so we have the parity checker comes out to be 1 for 0001, which is 1, and it comes out to be 1 for 00102, 2 for 4. So for 1, 2, and 4, it's 1, 1, 2, 4, and here it's 0. Then the next value of 1 comes at 7. So 7 is 1, 0, 7. Then we have 8 is 1, 10 is 1, uh, then 11 is 1, and 13 and 14 are 1. Okay. So we have 1, 1, 1, and a 1 here, and the other ones being 0. Okay, just a second, let's check this. Okay, yeah. So again, this is a chessboard configuration with alternating zeros and ones. So for this, we can write it as A XOR B XOR C XOR parity generator. So this is the variable parity checker. This is the variable expression or the Boolean expression for parity checker. So with that, we've come to an end of this chapter. So with that, we've come to an end of this chapter. I hope it was clear. So obviously the questions are not going to be direct like draw a full adder or write the truth table for a given combinational circuit. The questions would be like the questions we solved for MUX where we implemented a Boolean expression using a MUX, or like implementing half subtractor using using demux like we did, or implementing an adder using an decoder like we did, or like the multiple encoders which converted one type of data to another type. So these are the questions that are actually important. So I hope uh, you all understood these conversions and how they were done. And obviously, it's important to know about each combinational circuit and its working, because the questions will come in the form of implementing something in the using any combinational circuit of their choice. So I hope you all understood, and I hope this video was helpful, and I hope it helps you in the exam tomorrow.